So welcome back, everyone. It's a pleasure to introduce our first symposium about innovations in technologies to continuously monitor the brain in the real world. Our first speaker is Dr. Alex von Riemann. He's currently the head of the independent research group Intelligent Biomedical Sensing at BIFOLD, Machine Learning Department, Technical University of Berlin. He's also a visiting researcher at the Neurophotonics Center here at Boston University. His research focuses on machine learning and instruments for comprehensive brain-body monitoring. And the title of his talk today is fNIRS in the Everyday World.
Yes, okay. Well, thank you for the introduction. Is the time running? I usually talk very fast because I want to say too many things, so I need to keep the time in mind. Okay, so very briefly before starting, a little disclosure. So I'm currently consulting for fNIRS Medical Technologies. I'm not a shareholder, and my disclosure does not pertain to this presentation. So let's start. Actually, I would like to start with the vision that was developed by basically a lot of people present here a few years ago when I was postdoc at David's lab, which basically was in the end termed as neuroscience in the everyday world. And I want to briefly kind of remind us what the idea back then was, which is really what is happening now, because it has a particular kind of focus, which I personally I'm a big believer in, which is kind of multimodal. And we heard multimodal already before. What does that mean potentially for wearable brain-body imaging, and what are the challenges? And there's a lot of challenges. And but briefly, basically, we'll come back to this. The idea here was to combine a high-density fNIRS system that you have already seen David wearing, that didn't exist back then, with EEG, eye tracking, a scene camera, computer vision, and some machine learning, some data science to make sense of the data, to ideally at some point image the brain in the everyday world in naturalistic environments. And so this is why it's very exciting for me also to be here and talk. My PhD was trying to get multimodal instrumentation methods for new technology out of the lab into the everyday world. So this is basically just to kind of tease all the things that I'm not going to talk about, but that you will be able to talk with the PIs of this grant here at BU. So the idea is to investigate the brain during perception, interaction, and walking in the everyday world, to translate those findings from the lab into the everyday world, but also back to enhance our understanding how the brain works in the lab. And the three main application areas, not technology, we're going to talk about technology now, are what Swati will talk later about, that is a stroke and communication after stroke, abnormal gait and walking in Parkinson's disease by Alice Groen-Colomb and Terry Ellis. And there's a poster later on that I want to people encouraged to go to. And David Sommer's group looking at perception, attention, and working memory. So applications. So I'm not going to talk about applications, but I guess the idea is, as an engineer, which is in this case my background, what can we develop to enable more robust imaging, to enable better applications or better research with an application context. So yeah, on the hardware side, what we've seen, I think I'll start using this pointer because otherwise I'm going to just look at it. Yeah, all good. So what we've been observing, and I think everybody in the fNIRS field knows this, people new to fNIRS will be happy to learn that the amount of systems that are available as commercial systems that are available for wearable and wireless use have been increasing. Interesting now, and this is kind of a particular focus of this talk, is that systems, what does a system mean? An fNIRS system can mean one channel. It can also mean a lot of channels, as you saw on David's head. Specifically with a lot of channels going into diffuse optical tomography, with which we can reconstruct images of functional activation similar to fMRI. We also see that these devices are we're moving into a more wearable or at least portable realm. And so this year, again, there's a poster. It's going to be very easy to you to talk to David about this and the students in the lab. There's, of course, also other great endeavors like this rather portable device from Joe Culver's group. But as I already mentioned, there's also some commercial devices coming up that at least provide partial coverage of the head, or sometimes also full coverage, with a high density or a high number of channels provided in a high density. And so this enables us in quite some ways But before we go there, I kind of briefly, this is kind of how I want to motivate this talk. We also see already really commercial devices that are trying to reach the consumer market. And so there's some examples: the Muse headset for meditation, Mendy for so-called brain health. There's then, of course, the kernel device that is, I think, trying to potentially find several applications that are potentially interesting, not only for research, but also for consumers. And then there's companies that are doing, this is still research focused, but they're doing VR, EEG, VR, fNIRS, very clearly also with a goal to find applications in the consumer market. But the question is, the question comes in a second. What we see is there's a lot of investment, at least on the consumer side. So to briefly address what Joy talked about, I guess what we need to find is the investment on the research side. But I think it's encouraging to see at least that there's great interest in getting newer technology into into consumers' hands, but at least out of the lab. That's what we're all here for. So the question, though, is with all those things that I just showed, are we actually there yet? I mean, I won't judge whether those devices do what they promise, but I guess the question really is, be it for research or be it for consumer products and applications, what do we need to do to potentially get there? Okay, so unfortunately, the font is a bit changed. Look different on my laptop, but okay. So we have the three domains: instruments, signal processing, or methods, and the paradigms. I'm not going to talk about the paradigms. I already touched a bit on the instruments. I will try to now kind of tackle really a bit of the ongoing challenges and developments. First of all, of course, what we from an engineering perspective is what we want to achieve is we want to get a better better contrast. We want to measure the brain response to a stimulus. That gets more complicated with multisensory interaction and a lot of variance that is added to the signal. So the question is, how can we make sense of the variance in the signal? And then, of course, the signal that we do pull out, that we trust is actually brain, how do we link that with behavior and context? So this talk, I have three questions. I won't be able to answer them, but this is basically how I will try to lead through the different topics. The first one is, how do we obtain good signal? I'm going to go back a bit on artifacts that we've known for centuries, decades, sorry, not centuries, artifacts and fNIRS for decades, but also novel problems that we might have to face, and there are some solutions and some we have to devise. How do we improve contrast or explain variance? This is going into the machine learning, data science, new methods development direction, and then really more for discussion, how do we link brain activity with behavior? Okay, so let's start with the good signal. I'm going to show something old. This is a figure from David in almost 20 years ago. So just to show that fNIRS signal, and in that case, respiration and blood pressure signals measured simultaneously, that there is a relationship between those. And so since 20 years, we know that there's modulation in the fNIRS signal that is not brain, and we have to take care of that. And there are methods that do that, but this becomes more and more relevant in naturalistic interaction. I stole this figure that I find very pretty from Felix Scholkmann's paper from last year that basically tries to separate what compartments are contributing to the fNIRS signal. And that is, well, not only the actual brain response that we're interested in, but it is also cerebral and extracerebral contributions from vascular, from muscle, from systemic contributors, for example, blood pressure and the autonomic nervous system. And so this has been known, but it becomes more relevant because what we're interested in is this, and what we're not getting is this. If we walk while we measure our fNIRS system, we do a lot of stuff at the same time. And so the conventional methods from neuroscience, from fMRI and fNIRS neuroscience, would do general linear model analysis in a block paradigm, in a parametric design. And the question is really now that we go into the more non-parametric experiments and continuous experiments. Are there other methods that we can devise and that we can use to explain variance in the signal? I want to briefly kind of talk about three main sources of artifacts, you could say. So one of them is the physiology, so we'll come back to this. The other two are quite well known, but again, becoming more and more relevant when we start to move. So first is artifacts from optical coupling. This is kind of old story. So for years, when there's optoad shifts, people had to correct for that. Those optoad shifts can come from the cap shifting or the scalp actually shifting. So if you raise your eyebrows, if you talk and you have a cap with the chin strap, you create those shifts, and those will change they change, of course, they create an optoad shift, they change a change in the signal. Then there's also changes in contact pressure, which are not necessarily the same. So when you wear this optoad on an array of optoad, and for example, you walk and the whole thing doesn't shift, but the pressure onto your scalp changes, then you will see that as well in the signal, and that needs to be taken care of. This is three kind of short answers how to tackle this. So some of them are kind of already available, and it's just important to take care of this. And that is strain relief of the cables. Right now we have a lot of cables depending on the number of optoads. Now this is going in the engineering side, so I'm trying to reduce the weight further, which of course makes a huge difference. And then if not available already, incorporating spring loading of optoads to make sure that the optical contact and the pressure is supported. So this is optical coupling. Then we have something that basically was solved, or potentially, hopefully, still is solved, but becomes again more relevant now that we do experiments where the ambient lighting condition might change. So optical interference. So first of all, saturation. We're measuring very small optical signals. If you go into the sunlight, you have a lot of other light that goes into the head basically and scatters into the detectors, which can lead to saturation, but also demodulation artifacts from LEDs, from eye trackers, motion trackers that use near-infrared light. And so all of these are kind of new challenges. Some partial answers we have. So the overcap is one of them. Doesn't solve everything, but solves a lot to avoid saturation, also potential demodulation artifacts. Again, for the engineers that actually develop these detectors, it can make sense to incorporate optical filters, like bandpass filters, trying to block the wavelengths that we're anyways not interested in. And also, of course, we can look at smart demodulation, or so something that we haven't seen yet, but that might be interesting to see whether the system can adapt to modulation frequencies in the background that are creating interference. And so now we come back to the, I would say, actually greatest problem, but at the same time also the greatest opportunity, and that is systemic physiology. So the signals that confound our fNIRS signals that also provide a lot of potential info about the systemic state and the context. And so this is something that, well, we basically are still trying to figure out by measuring auxiliary signals. And that can be from context, but that can also be from the body. And then, of course, what we need to do is we need to find ways to incorporate that information into our methods. So try to depict this a bit more, again, from the same paper. I figure that I stole. What you see on the left is a typical hemodynamic response from a verbal fluency task over 2 different brain regions. And here you see 4 different signals. So that's mean arterial blood pressure, pressure of CO2, SpO2, so the oxygen saturation, the systemic oxygen saturation, and skin conductance. And so, well, what we see is that there is some co-modulation going on. And again, this can tell us a lot probably, but also it will probably confound, or in some indirect way lead to a systemic change in our measured fNIRS signal as well. And it will be important to take care of that, especially when this is here even in sitting and, let's say, controlled conditions, but especially when we move into more dynamic interactions, then we'll have to correct for that. This is an old experiment I'm always pulling up. This is from my PhD, but I still think it helps. So it doesn't really matter what happened here. It's a workload task. What actually matters is that this is the multimodal data that we measured, and every of these lines, we'll come back to these later on, is a button press. So we have time locked those. And what you can see is in the fNIRS and the accelerometer signal, there's quite some strong changes. And those changes, this is low pass filter, those changes are not due to brain response. We can see that it follows the motion that we acquired at the head, and then in EMG you can of course also see neck activity and so on. We'll come back to this, but basically just to show, of course it gets more tricky when we have a moving subject. What you see here is basically the average hemodynamic artifact across all participants and trials for a certain channel or 2 channels before cleaning and after cleaning. The cleaning is not so important here. I'll come back to it, but just to make clear, I mean, this is really the amplitude of our, or even higher than our normal hemodynamic response. Okay, so how to improve contrast, how to explain variance in the signals that is introduced, and this is, yeah, it's a very open question. So what I'm trying to motivate here is more like the general maybe way of thinking about it. The first statement is that incorporating physiology into the models improves performance. Very generally, I think that can be said. And so one of the methods that we developed that showed that in the GLM, in the general linear model, was that we could improve performance by incorporating amongst the short distance signals also acceleration, but also blood pressure and so on, into a data-driven regressor finder with TCCA. We'll come back, but the short story is just that the performance improved by adding more physiological information and adding it in a way that was useful to the GLM for regression. But this is also true in image space. So this is a recent paper from Yuan, I think, who's here, that showed that the simultaneous regression of short channel signals and the image reconstruction improves contrast. And then from the same paper that I know I've pulled already 2 figures from Felix Scholkmann and others for the network analysis of brain signals, you can see here now how contrast improves when to the regression information is added. So this is short channel, and this is additional systemic physiology. Okay, so clearly it helps, but the kind of give the details we need to figure out. And of course, as always, then the actual research question and also the application defines what coverage we need. But I think the general question is, of course, how dense and how many channels are usually really helpful to also help us understand what's going on systemically. What kind of signals, auxiliary signals, do we actually really need, which might really depend on the paradigm as well. And how do we model and find these complex relationships between those signals? And so we have heard already today machine learning, AI, pop up. This is of course, basically, because in all fields, there's great advances now using machine learning. In this context now, machine learning can be useful because it helps finding complex pattern and complex data. And we have quite complex data. We have multimodal, multivariate data with certain challenges that I'm going to briefly point out here. So the first challenge is that the latent components or the latent variables that we're trying to understand, they might be systemic, so globally in all channels with different delays. They might also be very local, so a certain variable, a certain process is not observable over all channels. That needs to be somehow taken into consideration. Generally, of course, every time we want to do machine learning, we need rather big data. The more data, the better, and in a structure that is comparable across experiments, because then if you want to transfer the whole method, let's say we find a perfect artifact rejection method, we need to make sure that that method doesn't only work for this specific data set with 20 channels and that specific auxiliary signal. And so this is a big challenge. There are some things that are going to help us, especially when we move into the image space with DOT, with diffuse optical tomography, because the image reconstruction already incorporates anatomical information from the head model to do the image reconstruction, which helps us separate scalp from brain better. And then also, if we co-register our sensors properly, and so there are several papers that use photogrammetry, and we reproduce some of this in our lab and found that we get quite some good results in very short scan time. Then, of course, we are able to move into MNI space, in which we potentially can compare much better across subjects and kind of move away from our channel space where the setup might be very different. So this is one. The second one is, I briefly pointed out before that we are more moving into the domain of non-parametric experiments, where maybe not everything is scripted. We don't always have the labels. We don't know necessarily what's going to happen when. And so the methods of analysis might need to change, or at least might need to be expanded as well. And so this is why I put here the unsupervised analysis, unsupervised data-driven using machine learning. What does this stand for? Well, it stands for the fact that we don't always have labels for our analysis, but maybe if we have multimodal data, the, let's say, sensor fusion approach helps us to make sense of what's going on in the data by relating those different physiological components. And well, the most obvious one is if we have our long and short channels in fNIRS, we know that the short channels don't see brain, right? We can basically relate those signals to make, improve contrast for brain. If we add other modalities, then that can be true as well. For example, to identify motion shifts and so on, without actually needing a label which says motion shift now. Okay, so challenges here. So there's quite some, and that is specifically because fNIRS and then multimodal physiological data, well, is let's say, yeah, is challenging in the following ways. That is that, again, latent variables. So basically what we're trying to find in the data that is not directly observable are often non-instantaneously and non-stationarily related. So they're not happening at the same time. Again, from the experiment, which I really show every time. I'm sorry for that, but I think it helps to make the point. Here, from this button press events that are time locked, you can see that acceleration and fNIRS signals are not instantaneously coupled. And so there's a delay, and this delay is not always the same over time and across channels. And so that's quite challenging for typical decomposition methods like ICA or PCA or whatever, because basically they assume instantaneous coupling. So yeah, the way we tackle this, and there's many others, but is modeling time shifts and doing temporally embedded canonical correlation analysis. This went into this GLM extension that I briefly mentioned before. Then we have other interesting, challenging characteristics, and that is that there are sample dependencies. Colored noise is not white noise, so it's frequency dependent. We have statistical dependencies, so it makes sense. We have physiological processes that we're trying to find and relate, and they are often dependent, right? So if I have a blood pressure change and a certain, in the motion, for example, one will lead to the other, and they're not statistically independent. And also, distributions are not always non-Gaussian, and this is all interesting because when you do ICA, which is, for example, quite often used in EEG for decomposition and rejection of eye movement artifacts, for instance, then in fNIRS, this by default doesn't work very well. So from the data from our experiment, these are button press events. Well, this is the source space. It kind of looks noisy. You don't really know what you see, but using more appropriate methods like the ERBM ICA that can model some of these dependencies, you get much cleaner decomposition. And so what you see here is, well, we have one source that's doing heartbeat, maybe there's two more, there's some low frequency components, and specifically we have 4 components that, oops, there was the wrong direction, that show these modulations from movement around the button press events. So this is basically where revisiting independent component analysis can be interesting, which was done in fNIRS quite a long time ago. And now that we have more channels with DOT and using the right ICA, this can be promising to tackle some of the statistical challenges. And lastly, nonlinear coupling, very important. Now that we're talking AI and most recently in the last years, very heavily deep learning, it will be very interesting to see what methods can be devised that model nonlinear relationships using deep learning. There's a recent review that shows the progress in the field of fNIRS using deep learning. How much time do I have? Somehow I don't see here I'm like 5, okay. Good. So then I want to briefly kind of lead over to the toolbox that we're currently building in the IBS lab, which is trying to kind of help a bit with this. So it's not yet there, it's not yet the solution, but it's trying to tackle the following. So we know there's a great many toolboxes for conventional neuroscientific analysis. There's also great methods and Python packages for machine learning. There's not yet really this kind of marriage of the two to devise new data-driven multimodal fNIRS methods. And so what we're working on is basically Sedalians, what we call it, a toolbox that is trying to kind of bridge this gap that integrates methods from available toolboxes with a framework that allows us to do data science, in using well-known packages, and doing this in an open modular architecture that makes it easy for others to contribute and also to get credited for it. And so this is really just in the drafts, but Eike, who's here, has a poster about this, is also happy to show you some of the, Jupyter Notebook examples that show just really, some of the considerations that went into the data structures here. Again, to say this toolbox is not ready, but we basically wanted to talk about it because it would be nice to get contributors and collaborators to move this framework forward to enable us finding methods that we clearly need. And now the last one is really more like an open and trying to be maybe outlook inspiring thing I have not much experience with. But again, with a particular focus of AI. So the first thing is going back to our original motivation, right? We want to go from this to this. Joy had this beautiful talk about it. And actually now, after what I just said, is I guess we want to also include this, so which is the physiological and environmental context in our analysis. This is the brief advertising for the lab. This is exactly what we're going to try to do in the next years. Basically develop methods for wearable sensors to exploit these multimodal relationships. all basically based around fNIRS. But now, what is already going on that is not really in our field, but I think potentially interesting. So there's two recent Nature publications that I thought I briefly just show here. One is Zebra, and Zebra is basically a deep learning approach that is using invasive data and like calcium imaging, but also a single neuron, plus behavioral data, and links those and finds learnable latent embeddings. So basically to jointly analyze behavioral and neural data. And so the idea is that you can use this for discovery, but also for hypothesis-driven research. And so this is clearly somehow something that seems to ring a bell when it comes to how do we relate our non-invasive brain activity with behavior. So just wanted to basically, I stumbled across this. I wanted to briefly put it out there that, of course, other groups and other fields are having kind of similar problems. This was animal research. And then you might know this one, which is basically a study with fMRI that did quite successfully semantic decoding using fMRI scans from people watching movies. So basically they created semantic context from the fMRI just by combining a large language model and the fMRI scans. And the interesting part here is really that the authors also looked at if you don't have fMRI and you reduce slightly the spatial resolution, like we would be able to do with fNIRS, and you only have cortical surfaces, would this still work? And basically the answer is that it still works. Not as good, but it still works, which again highlights why it is very interesting to move to image space and using DOT to really again try to find this bridge from fMRI to the everyday world. So very lastly, going back to our original figure, this is the right part of the figure, and this is basically just to say again, it would be really great specifically to hear from people that have experience in this. How to do proper eye tracking, how to do proper computer vision, how to do proper text-to-speech to create this automatic context and labels in our data continuously, ideally. So there are open source frameworks and basically what to use to not reinvent the wheel that has been already established in other fields. So that's kind of open questions that I personally would be really interested in discussing. And so with that, I'm done. I would like to thank really everyone in my lab, but also in David's lab and in the labs of the PIs in the Neuroscience in the Everyday World NIH project. And also I would like to briefly advertise this ongoing special issue at Frontiers. We just extended the deadline, advances in mobile optical brain activity monitoring. If you have something you would like to contribute, you have 2 more months and we would be really happy to receive your submission. Okay, thank you. And I hope I didn't go too much over time. Did 2 minutes. I see I still have.
So like we did before, people can come to the mic and ask questions, and attendees, virtual attendees should type their questions.
Hi, Alex. Thanks for the great talk. Like a quick question actually related to the question David asked Dr. Hirsch about like for the 2 boxes we're developing, like in general, how do we make it more, say, subject specific? Because you talk about the physiology and motion, and it can be different for different subjects. Like, do you have comments for those?
I have a very broad comment, which is basically the motivation for this whole multimodal, or was the motivation for this whole multimodal in the first place for me during my PhD, which is the following. When I say we need to explain variance, what I'm trying to say is, we have these signals across participants, across trials, across contexts, and we would like to find the common thing in them, right? And so the idea is that if we have multiple modalities, physiological context, but also other contexts, we might be able to improve our contrast in the sense that that works for single participants, for single trials even. And so my background back then was with BCI, so the whole decoding that was earlier asked, so the whole idea of can we, right, decode from a single trial in a single subject what's actually going on. And so I think that the great challenge is, of course, to find methods that can be translated. But at the same time, I think that if we include enough information, so if we do multimodal, that we will be much more likely that we can. And before I stop this long answer, one example, for example, in BCI, and particularly I think in workload and also neuroergonomics, is that BCIs that are trained on, let's say, EEG data can be very paradigm specific if people don't make sure that they remove the artifacts. So you might have a very good decoding accuracy, which is actually based on your paradigm because it's decoding how your eyes move in response to a certain task, not really how your brain activates. And so again, the idea is if you explain the variance in the signal, if you pull that out, you get more robust across different paradigms because you're looking at the actual brain response to workload, for example.
Thank you.
Hello. Thank you for the presentation. It was phenomenal. This is a bit outside of the scope of your presentation, so just keep that in mind. But the goal obviously is to move towards wearables that are present in everyday life. But unfortunately, we've seen companies kind of abuse, user information and data. And so moving forward, obviously, as we move towards this hopeful future of wearables, have you seen anything, or can you speak to, user agreements and, checking that, yes, I agree to all the terms and conditions, but not really reading through or company liability with that?
Yeah, so I cannot, it's a great question. I cannot say I've seen, that these examples that I think are the leading examples of how to do it. But I mean, there's a lot of discussion about this now, especially with AI coming and becoming better and better at decoding and, predicting. And so I think this is one of the big challenges, really, not only for brain imaging data, but with AI generally. I think there's so many studies that showed even your motion, and when you play with VR, the way you move can help to identify you. So very quickly. And so I mean, there's a lot in there. And I guess for us in research, let's say the concern is mostly how we deal with the research data, so that well, that's maybe potentially rather easy to promise, but then how to move that into actual applications is a huge issue. I've seen papers on this, but yeah, it's a good question. I don't have the answer.
Sounds good. Thank you.
Yeah.
Well, thank you very much for your inspiring talk. And I really like the idea of revisiting ICA because we have more channels than ever. But this may evoke another problem that, we may encounter unexplained noises as an independent component. Yes, and how do you deal with these problems?
Yeah, I mean, it's a great question. The whole interpretability, I mean, for ICA has always been, you don't even get the same order always, right? You don't know the exact amplitude. But then also for these deep learning nonlinear methods, I think, I mean, in machine learning, regardless of the fields, this is its own research field, right? Explainable AI. I think, again, so my take on this is that, for example, if we look at ICA components, and we don't know what those are, but they, for example, they correlate highly to a physiological signal that is clean that we measured. Right? Let's say you get this respiration component in fNIRS, but you also have your respiration belt. And they look pretty much, maybe time shifted, but pretty much the same. I think this is how you can start to make sense from it. And of course, without the ground truth, you won't know, but this would be, my take that I find actually incredibly exciting, because ideally we can pull components out that do give us more information on some latent processes.
Okay, thank you very much. Thank you.
Hi, Alex, great talk. There's a slide you showed earlier that got me thinking and a bit worried, because you're essentially showing that there are changes in these signals that are not time locked to the actual action. And I'm sort of asking a 2-point question, I suppose. One is, how do we then time lock? So, we know what the brain signal is. We know it's not related to the stimulus. It's related to some motion. How do we learn to do that more accurately? And then B, I suppose, and I think it's in your answer for Pepe's question, which is, should we be collecting all contextual data in real time to then use it to decompose, deconstruct what might be happening to the person and the environment? Like, how do we start thinking about that kind of stuff?
Yeah, it's a brilliant question. I mean, yeah. If the world was perfect, I would say let's get all the data we can later on, kind of try to make sense of it. To answer the first question, or to address it at least, so this is ongoing work, right? So the work that we did and how we solved it partially for the GLM extension is really via the temporal embedding of signals. So we saw there's this delay. We don't know the delay. This delay might not always be the same, but we can kind of add time-shifted copies of one signal that we know is causally related, so maybe always before, and then do the decomposition with that. So that's what TCCA is doing. And it solves some things and it brings some other problems, which is there's some parameters you have to tune. You don't know how many of these time-shifted copies, how long in total, and so on. And so I would say this is really the research that needs to happen, and that I think is really exciting on this kind of intersection of machine learning and actually understanding the data that you're doing the data science with. And so that's why I think this is an important part of the neuroscience in the everyday world. Lastly, these methods that are very powerful now, deep learning methods that are nonlinear, they need a lot of data. They potentially can model this and find these relationships. That's how GPT works with language, right? It relates, basically different words in the sentence to the context sometime before, and that is not always the same, right? So the issue there is just understanding. I mean, first of all, finding a model that works for us. Or several models, but then also understanding what's actually happening, and that's a big challenge in deep learning. But I think there's a lot of exploratory room.
Great talk. Thanks so much. Kind of to go off of another question that was the last session, talking about decoding, reverse inference, things like that. In your perspective, you obviously have a very good expertise on the methods and the design behind some of these things. To get to a level where we could, for example, use fNIRS signal to control a prosthetic accurately from a brain signal, something like that. Are we missing enough data that's reproducible and accurate together? Is it a processing thing, or is it precision of fNIRS data at this point? What do we need to get to in order to do something like that?
Yeah, I mean, I think there's many answers to that question. So first of all, I guess probably you would not control a prosthesis with fNIRS because of the delays. It would be too slow. Right. This is why Hassan will talk tomorrow about this, the neuroergonomics field, or these kind of mental state and those kind of things that are maybe potentially slower. Still, is something you want to decode. So same question, different application. I missed the second part. So can you remind me?
Yeah, totally. So just in general, would you say, like, in terms of getting more accurate decoding and reverse inferencing, is it more of a processing issue? Is it better AI models? Is it better data?
Yeah, I think it's so if you remember, there was this figure in which I said, like, we need to reduce variance and everything goes in there. It's hardware, it's methods, it's paradigms. I think it's really that. This is also what this field makes the field so challenging, also so interesting. Because, for example, if you have a system like David that you might show live at some point, you basically get a much higher, DOT, you get much better contrast by what the system itself offers before you do any, only very little, very well-known methods and signal reconstruction. So ideally, I think that should be combined with the additional information you have from physiology to then, let's say, at least improve the GLM, ideally improve unsupervised sensor fusion methods, and those have to be developed. So yeah, I don't know, it's not really a satisfying answer, but I think the interesting part is really that there's definitely several domains that can and have to be moved forward simultaneously.
Absolutely, thank you.